Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 3.11. A useful measure of an individual's physical condition is the fraction of his or her body that consists of fat. This problem describes a simple technique for estimating this fraction by weighing the individual twice, once in air and once submerged in water. Part A. A man has body mass MB, which equals 122.5 kilograms. If he stands on a scale calibrated to read in newtons, what would the reading be? If he then stands on a scale while he is totally submerged in water at 30 degrees Celsius, the specific gravity equals 0.996, and the scale reads 44 newtons, what is the volume of his body? Liters. Hint, recall from Archimedes' principle that the weight of a submerged object equals the weight in air minus the buoyant force on the object, which in turn equals the weight of water displaced by the object. Neglect the buoyant force of air. What is his body density? Let's start in writing the information that they gave to us. So we've got a mass of the body equals 122.5 kilograms. We know that the acceleration due to gravity is equal to 9.81 meters per second squared. So we know that his weight equals the mass of the body times the acceleration due to gravity, and this equals 1201 newtons, or 1202 newtons. Okay, we know that the specific gravity of the water he's being weighed in is 0.996. Okay, so now let's do our force balances and draw a picture here. So in force balance 1, we've got the man, and he's got his normal force in air, and he's got a certain buoyancy force in air. Now we're assuming that this is equal to 0, and then he has a certain weight of his body. And in number 2, this same person is submerged, and he's got a normal force acting on him in the water. He's got a buoyancy force acting on him in the water, and he's got the same weight. Okay, so those are our two force balances. So let's figure out how much. Okay, I'm gonna write my convention that all of the forces acting in the downward direction are negative, and all the forces acting in the vertical upwards direction are positive. Okay, so that means this weight actually becomes negative, and I'm going to write it as such in our force problems here. Okay, so this is our force balance number 1. We're going to say that the sum of the forces is equal to 0. Because if you're weighing the guy, he can't be moving. He can't be like jumping on the scale or moving up and down. We're assuming that these weights were done at steady state, so he's just totally still. So we've got the force, the normal force in air, plus the weight is equal to 0. So that means that the force, the normal force in air, is equal to the opposite of his weight, we figured out that his weight was 1,202. So, and the negative signs cancel out. So this force acting upwards, this normal force, is a positive force. Okay, let's do number 2. Okay, in our force balance number 2, we have 3 forces. We have the normal force in water, we have the buoyancy force in water, and we have the weight, same weight. And they gave us the magnitude of the normal force in water, because it says if he then stands on a scale while he is totally submerged in water, and the scale reads 44 newtons. Okay, so we know that scales don't read the weight force, they read the normal force, because the scale only reads whatever the equal and opposite reaction is to you standing on it. And that equal and opposite reaction to standing on the scale is the normal force. It's not the buoyancy force, because the buoyancy force equal and opposite reaction is acting on the surrounding water. And so the only equal and opposite reaction that it can be from standing on the scale is the opposite direction from standing on the scale is the normal force. Okay, so we know that the normal force is equal to 44.0 newtons. Okay, so that means and this equals 0. I should have written that down. The sum of the forces in a system that's totally not moving is equal to 0. There's no acceleration. Okay, so let's solve for the buoyancy force, because we know what the weight and the normal force are. So the buoyancy force equals the normal force minus the weight. We know that the weight is negative, and the two negatives make it into a positive, so that is the weight minus the normal force, which is 44.0, and this is all in newtons. So the buoyant force is equal to 1158 newtons. The buoyancy force is also equal to the mass of the displaced water times the acceleration due to gravity. And we also know that mass equals V times density, the volume times the density. So we can convert this into the volume of the displaced water times the density of the water times the acceleration due to gravity. And what we're trying to solve for is his body density. And his body density is equal to the amount of volume that his body displaces and his mass. So we already know his mass, so we're just trying to figure out what his volume is. And we've got a way to solve it right here. So let's solve for that. So we've got VW equals the mass, the volume of his body, which equals the buoyancy force divided by the density of the water and the acceleration due to gravity. Let's convert this into kilograms per meter cubed density, and then we've got per second squared. And this is all in SI units, cancel out, and we're left with meters cubed. And we get that the volume of the body is equal to 0.118 meters cubed. Okay, so that means that the man's density is equal to the mass of the body over the volume of the body, and that equals 1033 kilograms per meter cubed. Great, so now we know his density. Oh, but they asked in kilograms per liter, so let's just convert this into kilograms per liter. Divide by 1,000. So, okay, so for part B, it says, suppose the body is divided into fat and non-fat components. Okay, so if we're dividing this and we're assuming it, so we're assuming the volume of fat plus the volume of non-fat is equal to the total volume of the body, and that those volumes are separable. That's what we're assuming from that first line. And that this mass fraction, XF, is equal to the mass of fat over the mass of the body. And then we've also got this other mass fraction of non-fat over the mass of the body here. Okay? And then we need to prove that this mass fraction is equal to 1 over the density of the body minus 1 over the density of the non-fat portion, 1 over the density of the fat minus 1 over the density of the non-fat. So we need to prove this, where density B, density F, and density NF are the average densities of the whole body, the fat component, and the non-fat component, respectively. And then it gives us a suggestion of how to start doing this problem. So it says, suggestion, start by labeling masses and volumes of the fat component of the body and the whole body, and then write expressions for the 3 densities in terms of these quantities. Then estimate volumes algebraically and obtain an expression for the mass fraction in terms of the densities. Okay? So let's start off with this assumption that they gave us, that the volumes are separable. Okay, and we know that volume equals mass over density. Okay, so let's substitute that in. We've got a mass of fat over density of fat plus a... Then let's divide this equation by the total mass of the body so we can start working in the mass fractions. Okay, so we're left with 1 over the density of the body. Okay. We know, well, we want to remove this term. So one way to remove this term, I think, is to be able to know that the sum of the mass fractions needs to equal 1. So we know that this equals 1. So let's substitute this in for the non-fat portion. And then we have everything in terms of XF. So we need to separate our XF terms here. Shift everything over and put it in terms of the mass fraction. So now we've got 1 over the density of the body, what we were looking for. Yeah, okay, so we've just proved that that's what we're looking for. Okay, so yeah, if we start off with this assumption that the volumes are separable, we can arrive at the same proof that that this relationship exists. Okay. So let's do part C now. If the average specific gravity of body fat is 0.9 and that of non-fat tissue is 1.1, what fraction of the man's body in part A consists of fat? Okay, so let's just substitute in the specific gravities for the densities, and then we'll get the ratio. We'll get the ratio that we're looking for. So we've got XF equals 1 over, okay, so the body we said was this, so 1.034. 1.034 minus non-fat 1.1 over fat 0.9 minus non-fat 1.1. And this equals, that's our mass fraction of fat. Now let's do part D. The body volume calculated in part A includes volumes occupied by gas in the digestive tract, sinews, and lungs. The sum of the first two volumes is roughly 100 milliliters, and the volume of the lungs is roughly 1.2 liters. The mass of the gas is negligible. Use this information to improve your estimate of the mass fraction of the fat. Well, we know that the density of the body is equal to, okay, so we know that the density of the body equals the mass of the body over the volume of the body. Okay, but we just found out that we have to get rid of all these gases. So it actually, a better estimate is that it equals the mass of the body minus the mass of the gases over the volume of the body minus the volume of the gases. So this is a better estimate of what the true density is. So the density equals, this is a better estimate of the density, kilograms per meter 3. Okay, so then we plug this new density back into our equation here, and we get the new estimate for the fat is equal to 0.235. Okay, so that is it for problem number 3.11. Thank you for joining me. If you have any comments or questions, go ahead and leave them in the comments. Be happy to hear from you and try and help you out on if it's questions with this book or with another book or with another problem. Doesn't matter. You can just drop it in the comment section below and I'll see what I can do to help you out. Well, anyway, thank you for joining me, and I hope to see you in the next video. Thanks. Bye.